If you clicked on this video, it means you're probably interested in permissions for your AI or RAG application. Well, you're in luck, because in this video, we'll be going over all the ways to implement permissions in your RAG or AI application. Before we jump into each individual strategy, I want to do a little bit of background context into why permissions matter for AI applications. We've seen now more than ever, AI applications are putting third-party connectors, such as connectors to Google Drive, SharePoint, Salesforce, into their applications so they can understand their users' data better. For RAG, what this means is your AI application can query from your user's Google Drive or from your user's Salesforce and be able to answer questions with context from their organization's data or their individual data. Situations where you can query for sales performance from a teammate when you don't have access, that type of situation is not acceptable if you're building an AI application that's ready for production. So now that we've went over why permissions matter when you're building an AI application, let's jump into the strategies. The first strategy for implementing permissions when your AI application is performing RAG is by enabling third-party tool calls. If you're not familiar with tools, tools are how you can provide your AI application a way to run code based off logic that you give it. So usually how this works is you give a description of the tool when it's supposed to be used, and you also give the input parameters. To give an example of a tool, you might want to give your AI application the ability to query from Salesforce. What you do is you give a description. So the tool description might be, use this tool when your user asks about Salesforce contacts. You give it parameters for the function. You might give it a SQL query as a string format. And then lastly, you give code. And this is where your programmers and engineering team can actually write the code that your AI application will run. A lot of times with RAG and for querying third-party data sources like Salesforce, Google Drive, or Notion, this will be in the form of a third-party API call. The tool call will actually call the third-party API, get the response of that API call, and return it back to your LLM to answer your user's question. The advantage of using third-party APIs and tool calls is you're RAGing your user's third-party data, like their Notion data or their Salesforce data, and you're using the third-party API and passing your user's credentials. That way, you're essentially always going back to the source of truth, the third-party API, and getting the most up-to-date data. And because you're using the API with your user's credentials, you're also naturally always going to enforce permissions because the Salesforce API naturally has those credentials and permissions built in when you're passing in the API call. Some trade-offs from tool calling is that tool calls are not always performant. So you may have seen if you use Cursor or Cloud Desktop or any AI application, a lot of times your LLM doesn't always reliably call tools. Not only that, you're very reliant on the third-party API. So for example, if Google Drive doesn't have an endpoint that searches through file contents, you're not able to create a tool that is able to query from Google Drive. And lastly, tool calling isn't always scalable. If you're building an application with, say, dozens of integrations, say you have 12 integrations, and you want your AI application to be able to query from all 12 tools, from all 12 sources, that means 12 individual API calls. And this is a pattern that doesn't scale as you're building for more and more users across more and more third-party integrations. Our first strategy with tool calling is basically using third-party APIs and going directly to the source of truth. Our next three strategies are actually ingesting data from third-party data sources, indexing it into a vector database, and then performing retrieval from our vector database to perform RAG. This process is a little more involved, right? You actually have to pull the data from your user's third-party data sources, like their Google Drive and their Notion, and then store it and essentially have a second copy of that data in vector embedding format. While this is a very intense process, it provides coverage for a few of the trade-offs that I mentioned earlier. You're not relying on the third-party APIs. It's generally more reliable than tool calls. And lastly, it's more flexible. You're able to keep data from a bunch of different third-party data sources in one vector database. So our second strategy is using data ingestion, but now we're keeping all of our users' data in separate namespaces. If you're not familiar with namespaces, namespaces are essentially partitions in a database. We can use these namespaces to basically enforce permissions. Each user can ingest data and insert their data into their own namespace in the database. Then when they're interacting with your application, they can only query and perform RAG retrieval from data in their own namespace. This is an effective strategy if each of your users have very unique data and data is not shared across tenants. But as I mentioned, when you're building production apps, especially production apps for enterprise, normally you'll have a situation where your customer's admin will authorize data ingestion for their entire organization. This means that not every end user is granting access to, say, their Google Drive data, and instead, the organization is authorizing your AI application to process and ingest all of their Google Drive files as an organization. Where this gets really inefficient is in cases of data replication. So imagine that one of your customers, they have a company policy about vacation policy. This is a piece of data that every employee should have access to. And because we're using separate namespaces where each of your customers' end users have their own namespace and they can query from that namespace, this means that that vacation policy is now stored in every single one of your individual end users' namespace. This is a whole lot of unnecessary data replication. And then imagine all the work that needs to get done when permissions change. Say, for example, you need to delete that vacation policy in favor of a new one. Then all of a sudden, you need to update that vacation policy, remove it from each individual's end user's namespace, and then update the new one. That's a whole lot of data replication and operations that are just completely unnecessary. That gets us to our third strategy. It still involves data ingestion, but rather than keeping separate namespaces per end user, let's just make it simple and keep a separate namespace per tenant. And each of your tenant can be an enterprise. So we're not keeping separate namespaces per end user of your enterprise customer. We're just going to keep one database and one namespace per tenant. We'll perform data ingestion as usual from whatever third-party integrations that your application supports. But the trick is, if we're only keeping one copy of your customer's Google Drive, if we're only keeping one copy of your customer's external data, that means we also need to be aware of the permissions of that third-party data as well. So in this strategy, we're not only going to have to ingest their external data from Google Drive, from Notion, or from whatever, but we'll need to ingest permissions from every single piece of data that we process within our application. This way, whenever our end users are querying from our AI application, we are able to consult our permissions database and make sure that whatever data is being returned by our AI application, we're also going to check permissions and only return that data if the user has permissions to it. So one way to store that data is through an ACL, or access control list. Generally, access control lists are relational database tables where they can be as simple as having every single object that your AI application has access to, say every single Google Drive file or every single file in SharePoint, and then keeping a list of all users with access to that. Whenever your AI application is about to retrieve data and return it back to a user inside a RAG response, we're going to check with the file IDs and make sure that user is included in their access control lists. A couple things to be aware of when you're ingesting permissions. One, we need to make sure we have the infrastructure to support ingesting permissions data and also keeping that data up to date. So permissions aren't always static. Once we ingest all the permissions data, say from Google Drive, where we get every single user that has read access, write access, or ownership access to a file, we need to also implement either webhooks or polling to make sure we're always listening to permissions changes from the Google Drive API. The second trade-off that we have when implementing ACL tables is that we have to be really careful of modeling. In our simple example, where we just have one big table with all the data objects and a list of permitted users, updating and deleting data can be a nightmare. And the reason why is because a lot of integrations have very unique, nuanced behaviors. Say, for example, Google Drive. Google Drive has a very hierarchical permission structure. Users can be members of a team, and teams can have access to a folder, and folders then is a parent of a bunch of children files. So to figure out if a user has access to files, it's not always a direct relationship, right? You can't just query the Google Drive Permissions API and ask if a user has access to a file. Sometimes you have to go through a whole graph traversal to see if a user has access to a folder that's a parent of the file, or if a user is a member of a team with access to that file as well. And so whenever you're updating permissions data, this can get really complicated if you have a flattened ACL table. Say, for example, permissions changes on a folder, then for every single file that's a child of that folder, you're going to have to update that row. And so it's a really delicate process that you have to get right, especially for the permissions use case. There are a couple other ways to model your ACL tables, but I encourage you guys to check out our full tutorial in the description for more information. In the meantime, I'm going to go over our fourth and last permission strategy. So we went over ingesting permissions in an ACL table. In this method, we'll actually be ingesting permissions in a permissions graph. Data ingestion will still be done as usual and just storing it into a vector database and into a namespace per tenant. And so only one copy of our tenant's data is stored in our database. And we're still ingesting permissions data from the third-party APIs like Google Drive or Notion API. And we also need to make sure we have infrastructure to support detecting permissions changes, whether that's through polling or through webhooks. The reason graph databases are great for permissions is because they're very effective at writing and querying relationship-based data. And when you think about permissions, and we go back to our example of a user is a member of a team which has access to a folder which is a parent of a file, this is essentially like a graph traversal where we're making connections and detecting relationships between different types of objects that have permission relationships with one another. For graph databases, it's really easy to query and detect if a user is related to a file through a bunch of different relationships and hopping from, say, team to folder to folder to folder to file. And not only is it effective at querying, it's actually very efficient at writes as well. In my example where, say, permission changes for a folder, instead of going through every single file that's a member of that folder and having to change, say, that list with all the different user IDs, instead in a graph database, you really only need to change one edge, which is essentially one delete operation, where you delete the relationship between a user and a folder. So not only are graph databases effective for reads and for writes, but also it's extremely flexible. Unlike relational database tables with a very strict schema and constraints, graph databases are more flexible. We are able to put different types of nodes. So in my example, users, members, folders, files. But you can also have more types of nodes like roles and implement a role-based access control with your relationship-based graph database. And if your application is ingesting data from a bunch of different third-party data sources like Google Drive and Notion and Salesforce, you can keep all of that permissions within one graph. You can define a bunch of different node types that fit each type of unique third-party permission system the best. So in Google Drive, you have this whole hierarchical system, but in Salesforce, it might be a lot easier. Users might only have access to certain data objects, say a contact or a deal or a lead. And so you don't need to implement a whole bunch of different types of nodes with different relationships amongst them. That was a lot of background context on the different type of permission systems that you can implement. Let's jump into actually implementing our recommendation. The permission strategy we recommend, and the one we'll be implementing, is data ingestion with the permissions graph. To recap why we believe this strategy has advantages over the other three is compared to tool calling, vector search is generally more reliable and doesn't rely on the third-party APIs and whether or not they support text searching and semantic searching. 2, compared to separate namespaces, there's way less need for data replication. Rather than using namespaces to enforce permissions, we're keeping a database of all the native third-party permissions ourselves in our graph, enforcing it that way. And lastly, compared to ACL tables, a permissions graph is more efficient to identify relationship queries, which is generally what you want for permissions. With a permissions graph, we can identify relationships between a user and a piece of data even if the permissions have to propagate through multiple connections, such as having access to a folder and then that file being part of that folder. So now that we picked a permissions graph, there's actually two different ways we can implement it. And I'll describe the two strategies first before I will show you the implementation that we chose for this tutorial. The two methods are pre-retrieval filtering or post-retrieval filtering. And so when I say retrieval, this is all retrieval from the vector database. So it's what it sounds like. Pre-retrieval is essentially using the database to filter out all the objects that a user has permissions to. So an example that you guys might be familiar with is a SQL database where you have a where clause. So in this case, when a user authenticates and then asks a question, say they ask a question about sales data, based off the user, say it's a user named Jack, we'll go to our permissions graph and find all the data objects that Jack has permissions to. From there, when we go to our vector database, we essentially do a where statement and say, hey, give me all the vectors that have to do with his query, where the vectors have to be from a data source that he has access to. That way, our application backend doesn't have to do the filtering there and uses the database layer instead. The second strategy is post-retrieval, and it's essentially filtering after we already retrieved our vectors from our vector database. So in that same example, I still authenticate and our application knows that Jack is asking a question about sales data. We go to our vector database and just retrieve the top K most relevant pieces of data. From there, we go to our graph database and ask, hey, from these top K vectors, how many of these data sources does Jack have access to? And then the application backend does some filtering and only returns accessible objects to the LLM, which it uses to generate an answer and finally returns to the user. So both methods are secure and enforce permissions correctly. One is just using the database layer to filter out accessible objects and essentially doing the filtering pre-retrieval. And one is doing it post-retrieval where we're filtering out accessible data objects after the vectors have already been retrieved from the database. So now that we went over the two strategies, we'll be showing post-retrieval, where we're just going to use the vector database to receive the top K vectors from a query, and then consult our graph database and reconcile those permissions and access control in our application backend. So let's jump into the code. I'm going to open up my editor. Find where we're actually doing that retrieve context. And you can see I have an enforce permissions method. And in this method, we're essentially identifying relationships between data objects, a relationship, in our case, the can read, to see all the objects the user has read access to, and lastly, the user ID, which in this case will be email. From there, we're using Permissions API. Permissions API is a managed graph where Paragon keeps a managed permissions graph for us. It's part of a product called Managed Sync, which is perfect for RAG use cases. Managed Sync spins up data pipelines that sync our users' data, like our users' Google Drive, Salesforce, and all the integrations that we want. And the Permissions API essentially builds a permission graph of all the native permissions from those different integration providers like Google Drive and Salesforce. And then we're able to query that permissions graph via the Permissions API. In this example, I'm using an API called Batch Check, which essentially allows me to put all those different object relationship user queries and check multiple all at once in one API call. From there, I'm looping through the response of that batch check, which is essentially just an array of Booleans of whether that data object is allowed or not. And I'm only returning the ones where allowed equals true. So with that implemented, let's go back to our chat example where we're trying to query for sales data from a coworker. We're ragging data. And now this time, with permissions enforced, we can see we're not able to get data that we don't have permissions to. That was a whole lot on permissions, and we hope this video has helped inform you about permissions and maybe build permissions in your AI application. We encourage you guys to check out our full blog post below that we have in the description, and it'll cover all the topics that I just talked about, as well as other things about permissions that I might have missed, and we go into detail about more topics that we talked about today. We encourage you guys to subscribe and stay tuned for more AI tutorials that help bring your AI application from MVP to production. Thanks for watching, and see you in the next one.